Welcome to the first session of the nonlinear regression lecture. And let's start with an example. Let's suppose that you have some variable y that is a representation of a physical state. And this is let's say, a person, perhaps, some health state or something physiological that can be mapped. And we have a variable that represents whether or not the person has a voucher in order to buy medications. And then we have a variable that reflects the time that an individual is on medications. And let's suppose that the time an individual is on a medication is a function of the voucher. And let's suppose it's this function here, in which eta is a random variable with distribution f, whatever that distribution is. So let's assume that the rate at which the health state progresses with time is represented as t to some parameter lambda. Okay, and that might be as shown up here with this curve. We can separate the differentials, and we come up with dy is equal to t to the lambda dt, and we can integrate both sides and evaluate it at the time on medication. And we can come up with y is equal to the integral from 0 to t, capital T, our time on medication, time to the lambda dt, which if we do the integral, comes out to be this. 1 over lambda plus 1 times time on medication to the lambda plus 1. If we were to log lambda and then log this side, we will get the log of y is the negative of the log of lambda plus 1 times the log of our function that we had for t. So this is our main functional form for t, plus the eta term. Eta itself might be expressed as a constant times another term, which you can think of as an error term, where the expected value of epsilon is equal to 0. You can think of gamma as the mean of this particular random variable. So we convert it accordingly. And consequently, we may end up with a gamma minus log lambda plus 1 plus the rest here, plus an epsilon. Well, this is a nonlinear function in the parameters. Now the gamma and the log, or the negative log lambda plus 1, are all constants for a given parameter, and so we allow that to be a constant. And we allow, so we might have we can just call this whole combination here alpha, and this lambda plus 1, let me call delta, plus delta, times the log of this in here, just plug that in there, plus this error term. And we've got log y is equal to that, so that we have an equation that looks fairly close to what we might apply a regression or a least squares approach to. Only now this term right in here is the log of e to the beta xi minus 1, and so it can't be reduced any further. So it's a nonlinear function in the parameters, because there's a parameter right there in beta. So we have a parameter alpha, parameter delta, and then we have this parameter beta, which is in here. So we do not have the setup that we would normally do for least squared errors estimators on linear functions. And this is the kind of function, however, that we can use nonlinear regression to solve. So here is a general statement of that. General statement. So our general nonlinear least squares estimator. So we have a model of y as some function h of our independent variables and parameters, and then we have an error term. Expected value of the error term given x is equal to 0 is an assumption here for the estimates to be consistent estimates, similar to our ordinary least squares. But here, h is not necessarily a linear function, so we're allowing this to be, whatever nonlinear function that is identified, which we'll talk about later, but it's a nonlinear function. The expected value of y given h then is going to be h plus the expected value of epsilon given x, which we said was 0, so really it's just h. So this function is specified as the expected value of y given x. So the estimator is going to minimize the squared errors. So the error is the y minus its expected value, and I'll call that epsilon. And so if we take y minus h transpose times y minus h, we get our error transpose error vector, and this is the sum of squared errors. You can check if this works. This is the vector of random variables that underlie the data. It's with n observations, so it's an n by 1 vector. This also is expected value for each of those random variables. And so the error is also an n by 1, as is this one, an n by 1. And so when you take an n by 1 transpose times an n by 1, you get a 1 by 1, which is the quantity that we are trying to minimize with respect to theta. Clean this up a little bit. So again, you can look at the estimator. The estimator, the nonlinear least squares estimator, is the theta that minimizes the sum of squared errors, where the error is defined as the observed y minus the expected value, which is a function of the x's and a function of the thetas. A generalized form, generalized nonlinear least squares, similar to generalized least squares, is the same approach here, where this is my errors, and we're sandwiching that with a positive definite matrix W, a weight matrix. So with a positive definite matrix W, this becomes a generalized nonlinear least squares. So if we think to our usual least squares and our generalized least squares for linear models, the W is a way that we can handle weighting in various forms, including dealing with heteroscedasticity and such. But for now, the main point is it's really for any positive definite matrix. This is a generalized nonlinear least squares estimator. So this estimator, theta hat, is consistent, and it is asymptotically normal. And again, it does not have that property of having finite sample properties of being unbiased necessarily. So it is not generally known to be unbiased, but it is consistent and asymptotically normal. So to show the consistency argument, I'm going to do it in more of a schematic sense rather than go through a detailed proof like I did in the maximum likelihood estimator. So let's define then S of theta as being my sum of squared errors. It's the function I'm trying to minimize. So with some regularity conditions in terms of the mathematics underlying it, if the parameter space is compact, which means that the function h is continuous in theta and it's differentiable, if the p-lim of 1 over ns, or the average sum of squared errors, goes to a constant, as n goes to infinity, this quantity stabilizes. any particular other sample point, it was not going to throw it way out of whack once you're getting up to a really, really large number of sample points. And 3, that theta naught, our true value, is the minimum of q theta asymptotically, or this parameter that is the minimum of asymptotically is the unique value. Basically, I'm saying that this is identified. So with these conditions, the p-lim of theta hat is equal to theta naught. A sketch of the proof is essentially to say that the p-lim of theta hat is the p-lim of the argmin of 1 over n of s, which is the argmin of the p-lim of 1 over n of s, which is the argmin of q theta, which is theta naught. This is not a formal proof at all, but it's just kind of a schematic to kind of see roughly how we could get to the statement that the p-lim of theta hat is theta naught. The mathematical proof of this, similar to the maximum likelihood one, is a little more elaborate, but we're going to skip that for the nonlinear least squares. Let's go on to normality. The normality, let's define that S transpose is our first derivative, not transpose, S prime there. Double prime denotes the second derivative or the derivative of the first derivative. Similar to what we did before, we will start with the mean value theorem, and it states that there exists a theta tilde in between theta hat and theta naught, where the second derivative at theta tilde is equal to the first derivative at theta hat minus the second derivative at theta naught divided by the theta hat minus theta naught. And therefore we can come up with, by moving these equations around, the statement that the first derivative at theta hat is equal to the first derivative at theta naught plus the second derivative at theta tilde times theta hat minus theta naught. That's just the algebraic manipulation of this above. This here is equal to 0, right? Because it is the slope of the optimizing function at the value that optimizes the function. And here again we're considering that the maximum values are an internal point. And so theta hat, and so this equation, since this is now equal to 0, we can solve the equation and we come up with theta hat minus theta naught is equal to the negative of the second derivative at theta tilde, its inverse, times the first derivatives at theta naught. Multiply this by the square root of n, and we get the square root of n of this difference is equal to this quantity a times this quantity b. This is looking very familiar. This is exactly the strategy that we took with maximum likelihood, only that the terms are slightly different in terms of the function being optimized. Let's call this first term a and the second term b and evaluate each of these. So if it's the case that the p-lim of 1 over n times the second derivative at a theta converges to a constant matrix for all theta, and for theta naught, it's not equal to 0, which means that this is the matrix of second derivatives, and if it's not equal to 0, that means that it's not flat, which means it's locally identified. Second, if it's consistent, which above we said it was, then the p-lim of A is equal to negative that constant matrix Q at theta naught inverse, which is a finite positive definite matrix. Why is that? Well, that's because even though we're up here, we're looking at theta tilde, since theta hat goes to theta naught, and theta tilde is somewhere between the two, then it kind of sandwiches it in, and as theta hat goes to theta naught, theta tilde must also go to theta naught. So with a consistent estimator, it pushes the theta tilde to theta naught, and we can say that the p-lim goes to negative q theta naught. Okay, so now looking at part B. This is the second part up here. So we just evaluated part A, and now we're going to evaluate part B. So the 1 over the square root of n times the derivative of the sum of squared errors. If you look at the S itself, S was this, with my weight matrix in there, was the term where this is my error. I take the derivative with respect to theta, and theta shows up in the h function alone, we end up with negative 2 over the square root of n times the error, which is y minus h theta naught transpose, times the weight matrix, times the derivative of h with respect to theta. This is a term that I can call my error, epsilon, so I'll just rewrite it as the negative 2 over the square root of n times the error vector times the matrix times the derivative of h with respect to theta. This is a weighted average of error terms, right? And so we assume that as a weighted average of error terms, it is going to a normal mu sigma squared, and the variance of this term, if we take that, it has to do with this constant, and then my error or random variable in the middle. So I essentially, in a matrix sense, I square this term, and then I get the variance of the error, which is what I've got here. Right, there's my variance of the error, and this is squaring it, and then the constants come out squared, so it's negative 2 squared is 4, and square root of n is n. And my capital sigma here is my variance for the error term. Now, if the p-lim of this term goes to some matrix, what we mean is that, again, the variance asymptotically stabilizes to a particular matrix, and we can continue on. We'll see what happens. By the central limit theorem, 1 over n of the first derivatives converges in distribution then to a normal 0 4 times theta. That came there because this part is that part right up here. Oops, gotta include my n. This part. All right, so I still have the 4 here. So it's the 4 times the omega. And consequently, my square root of n of theta hat minus theta naught converges in distribution to the normal 0 and this quantity here, where I have my q theta naught inverse transposed and q theta naught inverse on this side, and my 4 sigma. Why? Because this term here is some variable that's a normal with this distribution, and above we said that this term itself converges to this quantity a times b, and b was going to this z, right? And so it's this constant squared is the variance. So this constant squared times the variance of z. This is not meant to be a z, it's meant to be a 2. And we said that that is converging to q theta inverse. So putting that together, we have our terms here. Now, if we look further, that the first derivative is equal to, of the sum squared error is equal to negative 2 times y minus h transpose the weight matrix and the derivative of h with respect to theta. And therefore 1 over n, the second derivative, is 1 over n, the derivative of the first derivative. And if I were to take the derivative of the first derivative, we get this term here, and you can look at that. It's basically going to take the derivative of this times that plus that times the derivative of that as how to do this particular derivative, and you will end up with this term here. However, the last term is reduced to this, which with the error term being independent of the h function, and more specifically actually of the derivative of the h function, this term then goes to 0, which leaves the p-lim of 1 over n times the second derivative as 2 times the p-lim of 1 over n, the essentially the gradient times, this is the gradient, times the weight times the gradient. So if we take that fact and plug it in to the above, we get the term here, which is what we had there. We square it, so it goes over to here. The 2 cancels with the 4 above, and then we have that middle term which we had above. Now, this is a term for the variance, asymptotically. If we let our weight matrix be the inverse of the covariance matrix, and if we're doing this from a pragmatic perspective, actual as an estimator, we can plug in a consistent estimator of this, and asymptotically this will bear out, because being consistent, it will go to the inverse of the covariance matrix. We will then end up with 2 of these canceling, leaving one of these with a sigma inverse. And again, this is now a sigma inverse, and the same thing goes over here. And one of these goes away, and the remaining term, if you look up above, is going to be omega inverse. So basically what we're saying is this, this whole fancy equation here, and notice that this Q is exactly this over here. It's just a shorthand for writing it, as I specified above. Essentially, if we let omega be the inverse of the covariance matrix, then this reduces considerably, and you just come up with the variance equaling to that omega above inverted. If you don't have the weight matrix equal to the inverse of the covariance matrix, then this is still legitimate up here. It's just a little more complicated, is all. It becomes much simpler when the weight matrix is the inverse of the covariance matrix. Okay. So, that being the case, we evaluated that variance up above, and it became this omega inverted. And so we ultimately end up with the square root of n times our estimator, theta hat, minus the true value, converges in distribution to a normal with a mean 0 and a variance of omega inverse. And again, that's the limiting distribution that is relevant. So we can kind of use it as a way of working out what we call an asymptotic distribution, which is a little bit of algebra. And you end up with the theta hat is asymptotically normal with the true value as its mean, and omega inverse divided by n as its variance. And this is the useful quantity that we use to do asymptotic statistics with, or that we can use. just as a technical point again, the limiting distribution of the estimator theta hat itself is a point mass. It's consistent as a point mass at the true value, which is why we don't use that. We use a stabilizing, a variance stabilizing series here, being the square root of n, or sequence, the square root of n theta hat minus theta naught. And that does have a distribution, no matter how large n is, to this quantity here. And then we just let that equal to, think of that as equaling to a normal z, and then we solve for theta hat, and we will have theta hat as a function of, it will be theta naught plus 1 over the square root of n z. All right, that's theta hat. And so the expected value of z is 0, so the expected value of theta hat is theta naught, which is what we just wrote there. And the variance of theta hat is the variance of this term, which is 1, the constant squared, which is 1 over n, and the variance of z, which is omega inverse, which is what we just have there. So it's a little bit of algebra. It's kind of, fooling ourselves in terms of the actual asymptotics, which is based on the distribution of this quantity, not the distribution actually of that one. But nonetheless, this is very, very helpful and reasonably accurate as the sample sizes get large. So now, that being the case, if we let E be IID, so that the sigma itself is an identity matrix multiplied by a constant, so it's homoscedastic IID, which is partly identically distributed, then we can restate the estimator as having a variance of sigma naught squared over n times a matrix G inverse, which becomes the p-lem of 1 over n, the outer product of the gradient. And this is really the basis for the walled statistics of just the standard basic model that we can run easily in Stata. Sigma hat squared can be achieved by the mean squared error of the residuals. G is the outer product of the gradient. And then again, W is the sigma inverse for the most efficient use of W, which, if you're going to come up and use this quantity, you're setting it equal to simply the variance times the constant variance times the identity matrix. All right, so that finishes up this first part of the nonlinear least squares lecture. We will then go on and look more at the estimator itself, what its properties are, in the following sections.